Hello my precious friends and welcome to our today's class. It is our second lesson on the 8th topic of Form 3 work, which is called heating effect of electric current. As usual, let me comment by giving the quote of the day, which states that to be truly successful, you have to develop the habit of going the extra mile. We shall discuss that quote at the end of our class today. So today we're looking at the applications of heating effect of electric current, and the first application we are going to look at electrical lighting, whereby our first application under electrical lighting is what we call the filament lamp. So this is a typical diagram showing a filament lamp. So it usually has the filament, which is usually coiled. Then in between that particular bulb, we usually have a mixture of nitrogen and argon. So the bulb is usually filled with a mixture of nitrogen and argon. So the function of the mixture of nitrogen and argon is simply to prevent the filament from evaporating. That is when the current flows through it. Then the filament is usually coiled so as to occupy less amount of space. So what happens is that when the current flows through this particular filament, actually that electrical energy or the current, the electrical energy is converted into light energy. Although some of the electrical energy is also converted into heat energy. That is why when you touch, that is a filament lamp, you will notice that when the circuit is closed, or when the current is flowing through the filament lamp, when you touch this particular bulb, you'll realize that its temperature will rise, or the bulb will feel somehow hotter, because the electrical energy, most of the electrical energy is converted into light energy, although some of the energy is lost in form of heat. That is to say, some of the electrical energy is converted into heat. In fact, we don't prefer using filament lamps because most of the electrical energy is actually converted into heat. So you find that such filament lamps will always consume more amount of power or more amount of electrical energy, because the energy that is lost in form of heat is usually large. Then the second application is in what we call the fluorescent lamps. So these are the preferred lamps. That is because they use fewer amount of electrical energy, or that is simply to say that less energy is lost in form of heat. That is for the case of fluorescent lamps as opposed to the filament lamps. So when the lamp is switched on, the mercury vapor emits ultraviolet radiations, which usually makes the powder on the sides of the tube to fluoresce, or simply to glow. So this is our typical diagram of a fluorescent lamp. I'm sure that these ones are usually very available in most schools and also in most households. So the apparatus involved, or some of the parts involved, one, we have the electrode. So we have one electrode and the other electrode here. Then we have the glass, which usually seals or usually protects the that is the apparatus that are within that particular, that are enclosed within that particular fluorescent lamp. Then in between we usually have the mercury vapor. Then on the walls we have the fluorescent powder. In most cases it is usually white in color. So most fluorescent lamps usually have some white powder, that is the fluorescent powder, which glows. That is when ultraviolet radiation meets it. So remember, these parts are usually connected now to the source of electricity. So when the lamp is switched on, the mercury vapor emits ultraviolet radiation. So in between here we have the mercury vapor. So when the lamp is switched on, or when the current flows through that is the electrodes, the mercury vapor emits ultraviolet radiation, so which makes the powder on the inside of the tube to fluoresce. So remember, when ultraviolet radiation, when they meet a fluorescent material, or a material which can glow, when it meets that particular ultraviolet radiation, this powder, the fluorescent powder that is usually on the walls of this particular glass, usually fluoresces, or it simply glows, hence producing what we call the visible light. So that is how a fluorescent lamp works, that when the lamp is switched on, the mercury vapor emits ultraviolet radiation, which when ultraviolet radiations meet a powder, that is a fluorescent powder on the inside of the tube of that particular that is fluorescent lamp, that powder, the fluorescent powder, it glows or it fluoresces. So to fluoresce is simply to glow or to emit what we call the visible light, which you usually use to observe some objects. Then it is worthwhile noting that different powders will produce different colors. For example, if you find a fluorescent lamp which has a white powder, that is the fluorescent powder on the walls. If the fluorescent powder is white, then the light that will be produced, the visible light that will be produced, will be white in color. If the fluorescent powder is yellow, the white produced with that is the light produced will also be yellow. So actually the color of the fluorescent powder determines the color of the color of light that will be produced by that particular fluorescent lamp. You'll find some fluorescent lamp maybe which are fitted with a fluorescent powder which is green in color. So if the fluorescent powder is green in color, then that particular fluorescent lamp is going to produce light, or the visible light, which is usually green in color. So the main purpose of the fluorescent powder is simply to determine the color of that particular fluorescent lamp. Then the other applications is in electrical heating. So the first application under electrical heating is what we call the electric cooker coil, whereby a plate or a coil is made of a high resistant material, and when electric current flows through it, the plate or the coil glows red hot. So remember here, these appliances simply involve conversion of electrical energy into heat energy. So they are usually made of a material of very high electrical resistance. Like they can use a plate or a coil, which is a material of very high electrical resistance, such that when the current flows through that plate or when the current flows through that coil, that current is resisted. So when current is resisted, that simply means the electrical energy within that is passing through that particular coil is going to be converted into heat energy. So a plate or a coil is made of a very high electrical resistance material, such that when the current flows through it, that electrical energy is converted into heat energy. So the heat energy is what makes those particular plate or coil to glow red hot. So that heat produced, or the electrical energy that has been converted into heat energy, is used to warm water and also to cook some food, or to increase the temperature of the material or of the liquid that is in contact with that particular plate or coil. Then the other application is in electric kettle, whereby an electric kettle has a heating coil which gets hot when current passes through it. So remember, if you observe electric kettles, at the base or at the bottom of that particular electric kettle, we usually have a coil. We usually have a coiled conductor. So that coil is usually made of a material of very high electrical resistance, such that when the current flows through that particular coil, it is actually resisted. So remember, when current is resisted, or when electrical energy is resisted, that electrical energy will be converted into heat energy. So that heat is what is used to warm the water and even cook even some tea or any other type of food that the consumer might be interested in. Next, our next application is in fuses. So a fuse is simply a short length of a wire of a material with low melting point. So for a material to be used as a fuse wire, the characteristic that that particular material must have is that the material must have a very, very low melting point. The materials that we use to make the fuse wires, we usually use tined copper. So that is, the copper material is usually used to make the fuse wire. And the reason why we use a tined copper is because copper has a low melting point. So which melts and breaks the circuit when the current through it exceeds a certain value, what we are calling the safe limit. So the reasons that can cause our copper wire or the fuse wire to break is short circuiting. The other reason that can cause our fuse wire to break is overloading the circuit. That is, connecting more electrical appliances that need more current as compared to the amount of current that has been set by that particular fuse to supply. Or when electrical appliances require a current that exceeds a certain safe value, what we are calling the safe limit. So overloading the circuit and also short circuiting is what can cause the fuse wire to break. So the breaking of the fuse usually saves the wiring from becoming hot and causing fire. So this is just a typical diagram showing our fuse, which is rated at 15 amperes, so it can only supply a maximum current of 15 amperes. So in between we have what we call the fuse wire, which usually melts when excess current passes through it. Then on the outer side we have the glass, which is simply used to protect the fuse wire. Then on the other ends we have the metal cartridge. On this other end we also have the metal cartridge. So this particular fuse is usually connected in between our source of power and of course the electrical appliances. For example, in this case we have an electrical appliance, which is the bulb, that requires or that draws a current of 14.9 amperes. So if an electrical appliance requires a current of 14.9 amperes, then the fuse that will be appropriate for that electrical appliance will simply be a 15 ampere fuse. So you can see that our fuse rating should be slightly higher than the amount of current which is being drawn by the electrical appliance. Because remember, if you allow a current of, for example, let's say 18 amperes to flow through this particular bulb, the bulb will actually blow off. It will blow off because the amount of current that it needs is only 14.9 amperes. So the fuse is there to ensure that a current which is far much greater than 14.9 amperes does not actually get to this electrical appliance. Because if a current, for example, of 16 amperes flows through this particular fuse wire will be heated. Remember, the electrical energy will be converted into heat energy. So that particular heat will cause our fuse wire to melt, because we have said it is made of a tined copper wire, which is a material of low melting point. Therefore, if excess current flows through this particular fuse, actually that current will cause the electrical circuit to heat up, and therefore the fuse wire, when the temperature increases or when the electrical energy is converted into heat energy, that heat will make the fuse wire to melt away. Then when it melts, of course, it will disconnect this circuit, or it will make the circuit to be open. Once the circuit is open, it means the excess current does not reach our electrical appliance. Therefore, the electrical appliance becomes safe. Remember, once the fuse has blown away, the only way to reset the circuit is to replace it with a new fuse, which has a fuse wire that is intact, or the one that is not blown away. Then we are saying that a 15 ampere fuse will blow out if a current of 15 amperes flows through that particular circuit, or if a current that is higher than 15 amperes flows through that circuit, then your fuse will actually blow away, because most of the electrical energy will be converted to heat energy, which causes your fuse wire to melt away, hence breaking the circuit. So that is to say that that the fuse rating should be slightly higher than the current drawn by the electrical appliance. And remember, the higher the rating, the thicker the fuse wire. For example, if you get a fuse which has a rating of 30 amperes, we expect the size or the thickness of the fuse wire to be actually large. But if you get a fuse with a smaller rating, for example of 10 amperes, we expect the fuse wire to be smaller. So that is what we mean by the higher the rating, the thicker the fuse wire. And remember, we usually have what we call the circuit breakers. The circuit breakers have an advantage over the fuses. The reason is because for a circuit breaker, once it has disconnected the circuit, you can just reset it. But for the case of a fuse, when the fuse blows away, you have to replace it with a new fuse. But for the circuit breaker, you simply come and reset. So that is the disadvantage of a fuse over a circuit breaker. So a fuse, once it blows away, it has to be replaced with a new fuse. But for the circuit breaker, once it is it cuts the current, or once it disconnects the current flowing through, you can simply reset without purchasing a new circuit breaker. Then let's look at an example. We are told that an electric heater rated at 240 volts, 3000 watt, is to be connected to a 240 volts main supply through a 10 ampere fuse. So determine whether the fuse is suitable or not. So the first thing, we'll simply calculate the amount of current flowing through that particular circuit, or the amount of current that will be required to be drawn by our electric heater. Then, because we are given the voltage and we are also given the power, remember from our previous class we did derive equations for the power, whereby we said that electrical power can be given by the product of the voltage times the current. So from this formula, because I need to find the amount of current that is being drawn by our electric heater, It simply means if I make current subject of the formula, current will be equal to power divided by the voltage. So the power, of course, I'm given as 3000 watt, then divided by the voltage is 240 volts. So therefore, the amount of current required, or which is being drawn by our electric heater, will be 3000 divided by 240, which gives us 12.5 amperes. Now, if you look at the amount of current that has to be drawn by the electric heater is actually 12.5 amperes. But the fuse that is connected is actually a 10 ampere fuse. So that simply means that this electrical appliance wants to draw more current than our fuse rating. Remember, if a current of 10 amperes or more than 10 amperes flows through this particular fuse, the fuse will actually blow out. It will blow out because that excess current will cause the electrical energy to be converted into heat energy, which will cause our fuse wire to actually melt out. Therefore, this fuse is not suitable for this electrical appliance. Therefore, the fuse is not suitable since the current drawn, that is the 12.5 amperes, is more than the fuse can hold. Remember, the fuse can only hold up to a current that is slightly less than 10 amperes. Next, our second example reads that find the maximum number of 75 watt bulbs that can be connected to a 13 ampere fuse on main supply of 240 volts. So because we are given the fuse rating, which is in amperes, so that simply means we'll find the amount of current that those particular bulbs will actually require. And because we are given 75 watt, of course this is power, we are also given the voltage, which is actually 240 volts. So we look for the formula that relates power, voltage and current, because we need to find the amount of current so that we compare it with our fuse rating, which is the 13 ampere. And we did say that power can be given by VI, that is electrical power. So to make current subject of the formula, I'll simply divide both sides by V. Therefore, current will be equal to power divided by the voltage. So the current that is required by that particular electrical appliance will simply be equal to, that is the bulbs will simply be equal to the power, which is 75 watt, divided by the voltage, which is 240 volts. So 75 divided by 240 volts, you'll simply obtain a current of 0.3125 amperes. Therefore, to find the number of bulbs which are required, we'll simply take the fuse rating, which is actually 13 amperes, divided by the amount of current that we have. Remember, this is the current for only one bulb. Therefore, to find the amount of current the amount of bulbs that will be appropriate for a 13 ampere fuse, we'll take the 13 ampere fuse divided by the current for each bulb. So if you divide 13 divided by 0.3125 amperes, you'll find 41.6. But remember, you cannot have 41.6 bulbs. So the number of bulbs need to be a whole number. So we are either talking of 41 bulbs, or if we round off to the nearest whole number, we can get to 42 bulbs. So if we try checking for 41 bulbs, if you take 41 multiplied by 0.3125 amperes, you will get that they need a current of 20, that is 12.8 amperes. But if you take 42 bulbs, you will find that if you take 42 multiplied by 0.3125 amperes, that is the current for only one bulb, you will obtain 0.3125 multiplied by 42, you will simply obtain 13.1 amperes. So 41 bulbs will need 12.8 amperes, but 42 bulbs will need 13.1 amperes. So if we compare these values to our fuse rating, the fuse rating is 13 amperes, then we said that the electrical appliance should draw the amount of current which is slightly less than the fuse rating. Of course, if we take 42 bulbs, these ones, they will require 13.1 amperes. And remember, 13.1 amperes is higher than our fuse rating. Therefore, if we connect a 13 ampere fuse to 42 bulbs, the fuse will blow off because the 42 bulbs will require a current which is slightly higher than our fuse rating, which is actually 13 amperes or 13.0 amperes. Therefore, the number of bulbs, the maximum number of bulbs that will be appropriate for a 13 ampere fuse will simply be 41 bulbs, because 41 bulbs will only require a current of 12.8 amperes. Remember, 12.8, we are simply obtaining it by taking 41 multiplied by 0.3125 amperes. Therefore, you can see 12.8 amperes is slightly less than our fuse rating, which is 13 amperes. Therefore, the number of bulbs that will be appropriate for a 13 ampere fuse will simply be 41 bulbs. Then I have an exercise here that I do recommend you should try at your own free time to gauge whether you have understood the examples that we have just dealt with. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that to be truly successful, you have to develop the habit of going the extra mile. So the quote is encouraging us to be hardworking in everything we do. It is also reminding us that nothing good will be handed to us freely. Instead, we need to work hard in order to acquire our dreams and also to achieve our dreams. Also recall that every successful person was once a beginner. Who never gave up on their dreams. Therefore, never give up, keep working hard. And lastly, remember that the only difference between ordinary and extraordinary people is just the word extra. Therefore, for you to be extraordinary, you have to do the extra work. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Until next time, this is Kind Tuition Academy.